Hello everyone. Today we will be discussing linear Diophantione equation. The linear Diophantione equation is of the form ax plus by equal to c. Let us discuss some brief history about this. The origin and early history of this. The name given for on the honor of this Diophantus, who is from Alexandria, 3rd century AD. He has written the book Arithmetica, and very first he studied about the integer solution of such type of equations. The earlier forms existed or known as in Babylonian mathematics, also in Indian Sulba Sutras, and from Chinese mathematical texts also we can see. As per the Indian contribution, we see the Brahmagupta introduced important identities for the integer solutions. Also, Bhaskara II refined the method and studied the Pell's equation. The Chakravala method, an elegant cyclic algorithm for solving Pell type equation, is also given. This type of equation also studied by some European mathematicians like Fermat. He expanded his studies of integer solutions of such type equations. He introduced Fermat's last theorem was proved in 1994 by Wills. Fermat's do a major contribution in the solution of Diophantione equations. Euler also made significant contribution for this, for solving the Diophantione equations. We know the Hilbert-10 problem during 1900. He asked the algorithm for general solution of Diophantione equation. But in 1970, it was proved that there is no such universal algorithm exist for the general solutions. I already told you that Andrew Wiles have proved Fermat's last theorem in recently 1994. The Diophantione equations evolved from ancient numerical puzzles to central topic in the modern number theory. Their study continues to the influence of algebra as well as logic and some computational mathematics. So let us discuss more about these Diophantione equations, some results, and if time permits, we have examples. So in the first slide, we have given already definition of this Diophantione equation. The linear Diophantione equation has the form ax plus by equal to c. These a and b must be integers and both should not be 0. That is the most condition of that. So like we have 3x plus 4y equal to 10. This is linear Diophantione equations. The coefficient constant ABC must be integers and x and y are unknowns. That if you find this x and y, let us this x naught. If you find x naught and y naught satisfying this, that means that x naught and y naught is particular or general solution of this linear Diophantione equation. Okay, let us discuss the important theorem regarding this. The linear Diophantione equation ax plus by equal to c has solution if and only if the d divides c. What is this d? D is the greatest common divisor of these coefficients of x and y, that is a and b. And more in general, if x naught, y naught find to be the solution of particular solution of this linear Diophantione equation, then these are the general solutions. This is the general solution of this in terms of particular solution x naught, y naught, where that t is an arbitrary integer. So let us prove this theorem in the next slide. So we prove in the two parts. This is first part, that will prove that ax plus by equal to c has solution. Then we show that the d, what is that d? D is the greatest common divisor of a and b. That d should divide c. Divide c means what? That c is multiple of d. And second part, if you get any particular solution of this linear Diophantione equation, all other solutions are given by this, where t is arbitrary integer. So let us see how it can be done. The part 1 will prove. So what was given in the part 1? That ax plus by equal to c is a given linear Diophantione equation, and GCD of a comma b is d. So what we have to prove? we want to prove that if this has solution, then D must divide C. So this is the two-way proof, if and only proof, necessary sufficient condition proof. So we have to assume that the Diophantione equation has solution. If it has solution, then prove that D divides C. Okay. So let Ax equal to By, Ax plus By equal to C has solution. And we want to prove that D divides C. So as we know that if GCD of A and B is D, that is D is the highest extraction from the number A and B, then there exist integers which are relative primes, R and S, special mention relatively prime. Relative prime means we cannot take any common from R and S. GCD of that R and S is 1. There exists integer R and S such that this A can be written as D times R and B can be written as D times S. So highest extraction from that number D is taken so that R and S have GCD 1. We cannot take on further common here. Okay. Then I will put this value A and B here. So A is D into R, B is D into S, Y equal to C. Let us take D common from here. D times Rx plus Sy equal to C. And what you see here? We see here that C is a multiple of D. This much multiple. C is multiple of D. That means D divides C. This is the one-way proof. Now conversely, what we have to prove? Conversely, we have to prove that if D divides C, if this D divides C, then show that Ax plus By has solution. So let us see how we get solution here. Now converse part, suppose D divides C. And what is this D? And D is GCD of A comma B. A and B are the coefficients of X and Y in that linear Diophantione equation. So as D is GCD of A and B, just right in the previous part I have mentioned that there exist relatively prime integers R and S such that A is dr and B is ds. We are not going to this part once again. We are using another result also. Since D is GCD of A comma B, there exist integers m and n such that GCD can be expressed as the linear combination of these two numbers A and B. This m n is found. From the division algorithm, we can easily compute what are the m and n so that D can be expressed as the combination of linear combination of the given integers A and B. So here you get you can that theorem gives us integer m and integer n satisfying this. Now what we want to show that we are given that D divides C, and we want to show that the given linear Diophantione equation has solution. Okay. So I will use this part. Given that D divides C, it implies there exists an integer t such that C is dt. So what I will do, I know D is here, the same statement I will multiply by t so that I can mention dt as C. So multiply by t to both sides. So this dt is MA plus NB multiplied by T. Let us apply the law of distribution in the set of integers for the multiplication. Since integers are commutative, they satisfy law of associative. After all adjustments, I will write this as A times MT plus B times NT. So value of this dt is C. So at last, I get C as A times MT plus B times NT. So this MT and NT are the values of x and y. We get solution x equal to MT and y equal to NT is solution of ax plus by equal to C. So in this way, we have proved that when D divides C, we get solution to the given linear Diophantione equation. This is the part 1 proof. Okay, we'll have the second part proof. We have to see what is second part. In the first part, what we have proved, you have given linear Diophantione equation. And we want to discuss the solution of this. When it will have solution? If greatest common divisor of the coefficients of x and y divides the right hand side constant part, then and then it has solutions that we have proved. This part we have proved. Now we want to prove that if we are able to find any particular solution condition, this is the solution condition. So whatever greatest common divisor of the coefficients a and b, that greatest common divisor must divide the constant part of the right hand side. Then and then your linear Diophantione equation have solution. Now once you get solution, you may call it as any particular solution you get, then all other solutions are found by using this statement. Here t is any arbitrary integers. Now this is the second part that we are going to prove in the next part second. Let x naught, y naught be given particular solution. Let x naught, y naught be given particular solution of ax plus by equal to c. This is the given linear Diophantione equation in which the greatest common divisor of a and b divides c. So what do you mean solution means? Solution means ax naught plus by naught equal to c. That whatever x and y found, x as x naught, y as y naught, if you substitute in that linear Diophantione equation, it must satisfy, that must be equal to the right hand side, that is c. Okay, let x dash y dash be any other solution to given linear Diophantione equation. What it means? This x dash y dash must satisfy the same statement, that is a x dash plus b y dash must be c. Now right hand side of these two are same, so left hand side has to be same. So I will write ax naught plus by naught is same as ax dash plus by dash. Okay, I will collect the same coefficient terms. I will collect y term to that side and x term to this side. So what I get? A times, okay, after simplification I will get this x minus x dash, this is equal to b times, okay. One more fact I have to use. We know that GCD of a comma b is d. So I will write here GCD of a comma b is d. That means there exist integers r and s. That two integers are related to primes, such that this a is, okay, I will write here, this a is d into r and b is d into s. This is a product where GCD of r comma s is 1. So use this fact here. So I will put the value of a and b here. So I get a is d into r, x naught minus x dash, and b is d into s. y dash minus y naught. Okay. Now this d is common to this. Like integral domain property, we can cancel the d from both sides. So after cancelling d from both sides, I will get this statement. Now focus on these statements. We are at the conclusion of the proof. As we see that r divides r into x naught minus x dash, because this number is multiple of r and that is equal to the other side. So this is equal to what I will write there, that r must divide s into y dash minus y naught. But as per the Euclid's lemma requirement, the GCD of r comma s is 1. So this r will not divide s. R divides the product of two number, but r will not divide s because s is relative prime to r. So it has to divide this number. That lemma is known as Euclid's lemma. So I say r divides y dash minus y naught. So one number divided other number means that other number is multiple of that first number. So y dash minus y naught is multiple of this. So what is the value of y dash? Okay, value of y dash is y naught plus r times t. In the statement, it may be given minus sign here, as I have considered this like statements. I can revise it as x dash minus x naught and y naught minus y dash. The other part will get negative sign here. So what I will do? I will put value of r. And what is value of r here? It is a upon d. In the statement here negative sign is given. It is because of you may consider this bracket as x dash minus x dash and then this bracket as y naught minus y dash. According to that, sign will change. Now while finding the value of x dash, we will get negative sign here. Okay. Once again I will say this term is divisible by s. Okay. So s divides s into y dash minus y naught. This implies s has to divide r times x naught minus x dash. Similarly, I will say that GCD of r and s is 1. So s has to compulsory divide this number as per the Euclid's lemma. That means x naught minus x dash is s times t. So this implies x dash is x naught minus s t. So if you go to the theorem statement, there is a plus sign because of only I have considered this. Okay, both are the same. So x dash is x naught minus, what is value of s? From here, the value of s is b upon d. So in this way, we get solution to the given linear Diophantione equations. What is the important condition? That the greatest common divisor of a and b, who are the coefficients of x and y in that linear Diophantione equation, must divide the constant part, that is right hand side of c. And these are the solutions. In the statements, sign may be given as different sign. Here plus sign, for y solution it has minus sign. Both are one. It is only by which case you are going to consider here. Okay. So this concludes the proof of this result. So okay, as I mentioned that x naught y naught is known solution and x dash y dash be any other solution, then one solution you get like this and this is another solution. While giving the proof, the sign has changed because of the considering of this term. That is also true. Thank you. In the next lecture, we'll be solve example on the linear Diophantione equation.